So in this problem, we're told that a population of values has a normal distribution with a mean of 6 and a standard deviation of 6.2. And we know that eventually we're going to draw a random sample size of n equals 55. So we have two parts of the problem. The first part is to find the probability that a single randomly selected value is greater than 7.1. And a second part, which is a little bit different, where we're actually looking for the probability that a sample of size 55 has a mean that is greater than 7.1. So these are different here. In the first one here, we're basically saying let's draw a random item from the original population and let's compute the probability that its value is bigger than 7.1. So the first step we need to do here is to calculate a z-score. So recall that a z-score is computed by taking the value that you have in front of you. In this case, the value is 7.1, and then subtracting from that the mean. And we know the mean here is 6. And then we divide by the standard deviation of the population, which we know to be 6.2. So in this problem, we know that 7.1 is the value that we care about. We'll put that here. And then the mean is 6. And then we're divided by the standard deviation, which is 6.2. When you do that, you get the following. The z-score is approximately 0.177419. So basically what this is telling us is that this value, 7.1, is 0.177419 standard deviations above the mean of 6. So in this problem, we're trying to find the probability that x is greater than 7.1. If we were to look at a picture of the distribution, essentially what we're trying to do is find the area that's over here. So right here at this point we have x equals 7.1, and we're looking at the probability that x is bigger than that, and that corresponds to the area of this curve right here. Now, finding the probability that x is bigger than 7.1 is equivalent to finding the probability on the standard normal curve, where the mean is 0 and the standard deviation is 1, of a z-score of 0.177419. So this probability here is equal to the probability that z is greater than 0.177419. So what we're going to do now is compute this probability. So now what we want to do then is think about how to do this. What we want to remember here is that the probability of z being greater than this number is equal to 1 minus the probability that z is less than this number. And the reason that we're doing this is because we have standard normal tables that will give us the probability that z is less than a particular number on the standard normal curve. So let's then pull up the standard normal curve tables to see what that probability is. But before we do this, please note that this value, 0.177419, has too many decimal places, so we're going to round it to 2 decimal places. And that's going to give us an equality that says it's equal to 1 minus the probability that z is less than 0.18. And this is what we're going to use on the normal table that we'll pull up here in a moment. So here's a portion of the normal table, and you can see here over on the left side we have z values that are approximately at 0.1. And because we have 0.18 here, we're also going to need to look at this column. So essentially, this is the probability that z is less than 0.18 on the standard normal curve. And so this gives me a result for my probability that says it's 1 minus 0.5714. And when I do that calculation, I get this. 0.4286. So if we go back to the original problem, let's go back to that here and pull that up. The probability that x is greater than 7.1 is equal to what we got on the previous page, and that is 0.4286, so just under 1/2. So the second part of the problem is a little bit different. Here we're being told that we're going to take a sample size of n equal 55, and we want to find out what is the probability that that sample size would be greater than 7.1. We're going to follow a similar process. That is, we're going to find a z-score and then compute the associated probability. But before we do that, we have to remember that because we're talking about samples here, the distribution that we're working with is the sampling distribution of the sample means. It's no longer the original population. So the first thing we have to do is compute the standard deviation of the sampling distribution, which is sometimes called the standard error. And here's the formula for that. We know the standard deviation of the sampling distribution is equal to the standard deviation of the population divided by the square root of the sample size. In this case, we would do the following calculation. We take the standard deviation of the population up here, and we divide by the square root of the sample size, which is the square root of 55, and we get 0.836. So this is the standard error of the sampling distribution. So now we can ask the question, how many standard deviations above the mean of the sampling distribution is this? Or actually is this number here. So here we have to compute another z-score. So let's go ahead and do that next. In this calculation, we're finding the z-score for the sampling distribution. So we're looking at the difference between the value that we care about and the mean, and then we're dividing by the new standard deviation, or the standard error, for the sampling distribution, which is 0.836. When we do that, we get 1.32. So what this is saying is that if we were to take a sample of size 55 and we found a mean of 7.1, that would be 1.32 standard deviations above the mean of 6 on the sampling distribution of sample means. But from this point, we can do the same exact calculation as before. We can calculate the probability that z is greater than this value by using the normal tables. So let's proceed to do that. So the probability that the mean of this sample is greater than 7.1 is equal to 1 minus the probability that the mean is less than 7.1, which is what the normal tables are going to give to us. So when I do this calculation, I get from the tables, you can look this up on your own, the probability that z is less than 1.32 is 0.9066. And so our final result is 0.0934, which is telling us that if you were to pick a sample of size 55, then there would be about a 9.34% probability or chance that the sample mean would be greater than 7.1.